All right, welcome back, guys. So, just continue from chapter 5. We're gonna move on to 5.2. Uh, so far, we introduce a general definition of probability distribution and discuss how to find the and standard deviations. We also touched on the range rule of thumb again, and I think that's about it. Oh yeah, we also discussed random variable, which is discrete and continuous. Um, to continue from what we left off in 5.2 and 5.3, we're going to focus on a specific um, probability distribution, and it's called binomial. So this is probability distribution that satisfies certain requirements that we call that binomial because it has two possible outcomes, and we'll be working with this for a bit. So this will cover discrete probability distribution, which is where the outcomes of a random variable that take up specific values or counting numbers. And then chapter 6, we're going to look at continuous probability distributions. So again, 5.2 focus on a specific um, random variable that has two categories for each outcomes, and hence why the name is binomial. So let's get to that. So the definition said that if x is a random variable that is discrete, then x can be modeled as a binomial random variable if the procedure satisfies the following criteria. Okay, so the procedure must have a fixed number of trials, meaning the procedure must have like 20 fixed number trial or 30, or the number of subjects selected from is 60 or 40 has to be fixed, right? The trials themselves must be independent. Each trial must have outcomes classified into two categories, right? And commonly referred as success and failure. And these are just the way we look at. These are just defined as the probability what we want to observe as we do this procedure considered to be success, and then what we don't want to see or what we're not observing considered failure. So it's not really quite the same meaning as success as being positive success. It's all depends on what we interest in, observing or picking from a procedure or the outcome, from the procedure itself. The last requirement, the probability of success must remain the same in all trials. So, if a procedure has these four conditions met, then we can consider that procedure to be a binomial random variable. Um, so it said the procedure satisfies the four requirements or distribution random variable x. The number of success trials and trials is called a binomial probability distribution. So it must have these four conditions here. So example one, we kind of look at few examples that what does it mean to have a procedure or experiment that satisfy the four conditions, and then we can say, okay, this experiment or this procedure considers to be a binomial probability distribution or just a binomial random variable. And it said if for those are not binomial, identify at least one requirement that is not satisfied. Okay, so let's start with the first one. If we have experiment or procedure that flipping a coin until we get the first heads. So, if you could flip coins, you could get heads on the first toss, or another student that is not lucky. So he or she can take 10 or 15 or 20 toss until they get first head. So we don't know, in this case, is the same for everybody. So in this case, we have a procedure that is not a random, not a binomial random variable. Why? Because it fails the first requirement. It doesn't have fixed number of trials, because it does not have a fixed number of trials, right? Number of trials. So because it could be different from a person to another person. when we carry out the experiments. Part B is that in a consumer reports, 427 different women are randomly selected without replacement, and each woman is asked what she purchased online. Response consists whether clothing was identified. So this here, responses consist whether clothing was identified. It's either clothes were identified or not. So that gives us the two categories, success or failure. But what makes this fail, what makes this not a binomial, not a binomial random variable, is that the selections themselves is dependent. The selections are dependent because it's without replacement. So that changes the probability of success for each trial. So we say that not binomial random variable because selections without replacement will change the probability of success for each trial, or the trials themselves are not independent, right? So if we have selections without replacement, by definition, that means the sample space size keep changing or keep decreasing. So therefore, they're not the selection are not dependent. Not independent. Therefore, they're dependent. So that's one of the requirements here, is that the trials must be independent. All right. The third one, sometimes some of this thing where we just have to have some sort of assumption that it's not quite written out in the problem here. For example, in part C, it said in a U.S. cellular survey, 500 smartphones users subject were asked if they find abbreviations such as LOL or BFF annoying, and each response was recorded as yes or other. So this gives us two categories, success or failure. And it doesn't say anything about like the subject were selected. It just say 500 smartphone user were asked. So in this case, we're gonna assume that the requirements are met for this this procedure here. So it is a binomial variable. Okay, and then let's go through the list here. It has fixed number of trials. Okay, so it has fixed number of trials because there are 500 smartphone user, and then the trials are independent. So this is where we have to assume here. So assume, because it just say 500 smartphone users were asked. So it didn't say anything about like selections or picking anything like that. So we're gonna assume that the selections are independent. The third condition, so it's a each trial, each subject has two responses. Each trial has two outcomes. So either yes or other. So those are the two categories. The last condition is said again. So nothing saying anything in here about the probability of success. The selections are without replacement or with replacement. So we're gonna have to assume this last part as well. So we're gonna say the probability of success is the same. So we're gonna assume this as well. So this one's kind of a weird one there. Sometimes there are some part where we just have to assume that it satisfies the condition. But the two main ones that we're concerned about is the fixed number of trials and the two categories. Those tend to be the most the what come across quite a bit when it comes to identify a certain procedure that considered to be binomial probability distribution or not. Is condition 1 and 3 there. Okay. So the next example will introduce us the binomial probability formula. This allows us to calculate the probability of any event occur from a binomial probability distribution. So it's useful to have a formula to help us figure out the answer. So exercise 2 kind of allow us to see or appreciate why our formulas were developed to solve these type of problems. Otherwise, do by hands, it could take a lot longer than we want. So it said Mark is taking statistics tests and there are 5 true/false questions need to be answered. Unfortunately, he did not study and is going to guess the answer by randomly marking them true or false. Let X be the number of correct answer using the guess technique. So first of all, it said for each question, how many possible outcomes? So we're gonna say 2 outcomes for each questions. Right, either true or false. Right, so in this case, success or failure. And success means guessing a question correct. So that could be true or false. We don't know. True means correct or false mean correct for each question. And then in this case, failure is guessing a question incorrect. Okay. Let's see. Find the probability of guessing exactly 3 questions correct out of 5. That is, find P of X equal to 5. So this would be capital P there. For this question here, let me just kind of sketch out what this question is asking. Okay. So let's call this S and then F for S for success and F for failure. So if we want to find the probability of X equal to 3, so this is asking for, the probability of guessing exactly 3 questions out of 5, right? So in order for us to do this, right, we need to figure out how many outcomes are there, total outcomes in the sample space. And the sample space in this case is the procedure of, guessing, 5 true/false questions. Okay, and then to figure out the probability of guessing 3 out of 5, right? We need, on the numerator, we need to figure out the number of ways a student can guess, guessing exactly 3 questions correct out of 5. Okay, all right. So to answer this question, we need those 2 things. We need the numerator, we need the denominator. So for the denominator, we know that from the previous chapter, each question has 2 outcomes, 2 possible outcomes, and there's 5. So we're looking at 2 to the 5th for the denominator. There's 32 total outcome for this sample space. How do we figure out the numerator? Okay, how many different ways we can guess 3 questions correct out of 5? Well, we can try and listen them here. We can try to listen them. Okay, so we can say, all right, let's try to list how many different ways we can have 3 questions correct out of 5. So a student can guess the first 3 questions correct, so success, and then the last 2 questions wrong. So we have S, 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 F, F, F. So that's one scenario for a particular student. Another student can guess, the first 2 questions right, and the third one's wrong, and then the fourth one's right, and then the 5th one's wrong. So that's another possible outcome as well. And then you can get S, F, S, S, F, or you can get F, S, 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 F. So that means the student can have the first and last question wrong, and then guess the 2 middle question right. Now, if you do this correctly, if we sit here and we list all possible way of guessing 3 questions right out of 5, there are going to be 10. There's going to be 10 possible way you can guess 3 questions correct out of 5. Now I only list 5 here. I'm gonna let you guys find the other 5 on your own. Just go ahead and just give that a try. So there should be 10 total. It's not gonna be easy, okay, but for the sake of saving time, I'm gonna let you guys work that out on your own. The point of doing this is we don't have to do the listing by hand all the time, because what if a procedure that involve guessing 10 question correct out of 30, and each question true or false. So we don't want to waste a lot of time just sitting there and list out by hand. It turns out the formula for this is going to be NCR, number of combinations out of N, and choose R. Okay, so in this case, it can be 5 choose 3. 5 questions, we want to guess 3 right. So it's gonna be 10. I'll show you guys how to do that in the next video. So that's how we get 10 here, right? But you should practice, you know, this one out. Let's guess to see if you can list out all 10. It's a fun activity. Anyway, so the answer for this one is 10 over 32. So if a student didn't study and guessing all 5 questions, so the probability of getting or guessing, you know, 3 correct out of 5 is what is 10 over 32? So that's 31%. Okay, so to get 3 out of 5, 3 correct out of 5, and that's not even 70%. That's not even passing. So try this on your own here. Actually, we'll come back to this here. We'll come back to try fit out guessing 4 out of 5 correct, because that's when you pass the quiz there, right? So what is P out of x equal to 4? We'll come back to that question, right? If a class doesn't study for a quiz and we want to figure out what's the chance of the student guessing 4 questions out of 5 correct to pass the quiz, because 3 out of 5 is not even 70%. So 4 out of 5 will be 80%, I believe. So that's going to be a lot lower. The chance of that is going to be a lot lower. So that's something to think on the side there. I'm going to go ahead and pause on this video, and then we're going to continue from this video on the next one.